Aloha, Richard Halverson here, and this is ITS128, and we are in Chapter 6, and this is the second time I've had to record this video. I'm going to make sure my sound is on. It's on. Okay. All right, so I'm sharing my screen. We are in Chapter 6, and this first video, I'm going to do three videos for this chapter. The first video is going to be this quiz 6.2. The second one will be the second two quizzes. They're very short, actually, very easy. And then the last video will be on the projects. So let's get started on the on this first quiz here. And we're learning about functions now. Now, we have used functions. The printing is a function, input is a function, int. Those are functions where we have an input. We have input parameters, possibly, and then it returns a value. And so but we can define our own functions, which is what's nice about this chapter. Here, for example, we're defining a function called max. And this function will return the larger of two input parameters. So the first thing it does is it checks to see if the first one is larger than the second one. If it is, it returns the first one as the answer. Otherwise, it checks to see if the first one is not larger than the second one, then it returns the second one. And it sets result equal to the second one, and then at the end it returns this result value. So the result value is either going to be equal to num1 if num1 is larger than num2. Otherwise, it's going to return num2. All right, and to invoke the function, it looks just like this. And you see this return thing means it returns what the value is. So that's what the value is going to be. This value of that whole thing is going to be the larger of this number or this number, and that will get stored into Z. Okay, so you should read through these and take these little questions here, answer some of these. It'll help you get going here. And let's get started with the quiz. Question 1 is we are on question 1, and write the definition of a function called typing speed. So it's a function. It's got two parameters. Function called typing speed, and it's got two parameters. The first is a number of words that the person has typed. So I'm going to say num words, say. And the second is the number of words that the person typed in a particular time interval, in some number of seconds. And the second parameter is the actual number of seconds. So it's the time interval. So the second parameter is going to be an integer number greater than 0. And the first parameter is also going to be an integer number greater than 0, representing the number of words the person typed. And so this function is supposed to return the typing speed. Okay, so the first parameter is the number of words. The second parameter is the number of seconds. Call it that. And so we're going to return the number of words divided by the number of seconds, divided by the number of seconds. That gives you the number of words per second. The number of words per second. So if you can type one word per second, then you multiply that by 60, and that's the number of words you get per minute. So you take the number of words per second, multiply that by 60, and that gives you the number of words per minute. So we just need to multiply this whole thing by 60, and that should give us the number of words per minute. Number of words per second. If the guy can type 2 words per second, that's 120 words in a whole minute. So we're just multiplying that number by 60. So the result is going to look, we have to put a def statement in front of it. And so our the answer is going to look something like this. This is a function which, when called, will return the number of words per minute. All right, what's next? Write the definition of a function called twice, and it receives an integer parameter, and it returns an integer that is twice the value of the parameter. So definition of a function called twice, and it's going to receive an input parameter, call it I, colon, and it's just going to return twice I. It's going to return 2 times I. So return 2 times I, something like that. Quite simple. Question 3. We're going to define a function called add, which receives 2 integer parameters and returns the sum. So this is a very simple function. We're going to call it add. It's going to input 2 numbers. It's called I and j, and it's just going to return the sum of them. So return I plus j. Returns the sum of the 2 integer parameters. So that, something like that. All right, question 4. Write a definition of a function called max that inputs 3 integer parameters and returns the largest. So we've got a function called max, and it inputs 3. Let's call it I, j, and k. And so we just have to look at all the numbers. Let's look at them all one by one. Let's start out by defining a variable called m, and we can set that equal to I. It's the first one. And then, so right now, and I will store, and m will store the maximum number. So right now, m is equal to I. Let's see if j is greater than m. If j is greater than m, then we want m to equal j then. If j is not greater than m, then we want to leave m as it was. If j is greater than m, we set m equal to j. All right, so after this, we will have the greater of I and j in m. All right, so we still have k to check. So if k is greater than m, then we want to set m equal to k. All right. So at this point, we know that m is the greater of I and j, and then we check k, and if k is greater than m, then we set m equal to k, and we now know that m will be the greatest of I, j, and k. And so with that, we're going to just need to return m, and that's going to return the max. You can try that out, see if that works. And now we're looking at another function called power2. Making sure I'm still making some sound here. Write the definition of a function called power2, which receives 2 parameters. And the first is going to be a float, and the second is an integer. So what this function does is, if the second parameter is negative, then it just returns 0. Otherwise, it returns the value of the first parameter raised to the power of the second parameter. So in other words, we've got this function, power2, and it's going to take in 2 parameters. It's going to take in a floating point number, and it's going to take in an integer. I'm going to use those variable names, doesn't matter. And we're going to return we're going to return the value of the first parameter raised to the power of the second parameter. So let's, so we're going to just return, I'm going to put this here, return. We're going to return the first parameter raised to the power of the second parameter. That will work. F raised to the I power. Okay, but we aren't going to do that all the time. If I is less than 0, we want to return 0. So let's, before that, let's put if I is less than 0, then return 0. Okay? Otherwise, return F times I. We need to do, I think this will work just the way it is. I don't think we need to put an else in there. All right, so anyway, you can try that out. You can also try putting an else in here, like this. And when we do this, we got to make sure the tabs are right. We got to make sure that these are counted the same. So I'm just going to tab, 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 tab. All right, something like that should work. Let's try question 6. All right, assume we have this function called is prime. Okay, so this is a function where okay, so this prime, this has one parameter and it's going to return true if that parameter that is passed is a prime number, and it's going to be false if that parameter that it was passed is not a prime number. And so we're going to have another variable called n, and we're going to write statements needed to find out how many prime numbers you can add together before when the sum that we're adding goes over the value for n. Okay, so that means that if we have some value, let's say n is 10, and we want to add 2 plus 3, I'm looking at the prime numbers here, 2 plus 3 is 5, plus 5 is 10, plus 7 is 17. Okay, that's too big. But when we had 2 plus 3 plus 5, that equaled 10, and so that would work. So if n is 10, and we start adding numbers, up to the point that the total, before the total exceeds n, so we can get up to 5. We can get up to this prime number there, and it has not exceeded 10, but if we go one higher prime, it will exceed 10. So we're counting prime numbers, so that number is 3. There's 3 of them, so we can add 3 prime numbers together, the first 3 prime numbers, and it will not exceed this value 10. But if we add one more prime number, it will exceed the value 10. So when n is 10, the answer is 3. If 10 is 17, the answer would be 4, because we could add a 7, and that is equal to 17, and so the answer would be 4. If it were 16, this would exceed 16, so the answer would still be 3, because we can only go up to the point before the total exceeds n, and if we add 7, it would exceed 16. So this is a pretty difficult question, and it turns out it's tough to test this because we don't have a function called is prime. Turns out that at the next question here, question 7, we are actually asked to create a function called is prime. Is prime receives an integer and returns true if the argument is a prime number, otherwise it returns false. The way this function works is an integer is prime if it is greater than 1 and cannot be divided evenly. In other words, there's no remainder when you start dividing all the numbers underneath it. So you have some number that you're testing to see if it's prime. You divide that number that you're testing by all the numbers underneath it. And if anytime you divide, except for before you get down to 1, okay, if anywhere down to 2, you divide, and you end up with a remainder of 0, then you know that that number is divisible, that the number you're testing is divisible by that number because the remainder ended up being 0, and so the number's not prime. So what you need to do is when you're testing for a number's prime, if a number is prime, you divide by all the numbers underneath it all the way down to 2, from 15, for example, all the way down to 2, and every time you do it, you end up with a remainder of not 0, and you go all the way down, then you know the number's prime. So if we take 15 and we start dividing, we divide by 2, it's not a remainder of 0. But if we divide by 3, it is a remainder of 0, because 15 divided by 3 equals 5 with no remainder. 13, on the other hand, is prime, because you can't divide it by 2 and get a remainder of 0. You divide by 3, you don't get a remainder of 0. 4, 5, 6, 7, 8, 9, 10, 11, and 12. You divide it by all those numbers, and not once is the remainder going to be 0, and so you know that that number is prime. Okay, so that's how the algorithm works. Let's try to write the function. And what I'm going to do is I'm going to open up another text file here, and I'm going to save it as a test.py on the desktop. And I'm going to start writing some code here that I think might be able to figure out how a prime number works. Let's see. I'm going to define a number is prime. Define a function called is prime, and it's going to take in some number I. And what I'm going to do is I'm going to start out so let's look at I. If I is less than 2, then we know the number is not prime, because the prime number's got to be 2 or bigger. So we say return false. This number's not prime. Otherwise, if the number is greater than 2, let's start with 2. Let's start with so let's start testing other numbers starting at 2. I'm going to use j as the test number. We'll start with j equals 2, and we're going to go all the way up to I. So while j is less than I, then we want to test to see if we can divide I by j and see if we get a remainder of 0 or not. So if I divided by j, the mod j, because we want the remainder, we don't want the quotient. So we want to take I divided by j, and we want the remainder. So this is how you write that. If I divided by j remainder is equal to 0, then we know that we don't have a prime number. That's like if we have 15 divided by 3. We have 15 divided by 3. We're going to get 0. It's going to be a quotient of 5 and a remainder of 0. So then we know that 15 is not prime, so we want to return false again. Otherwise, let's keep going, because we have to go all the way up to I. So let's increment j. So we go to the next j. So we start out with 2, and we test it. 15 divided by 2 is remainder of 1. So it's not a remainder of 0. So then we add 1 to 2 and we get 3, and we come back around and we test if 15 divided by 3 is remainder 0, and it is remainder 0, so we're going to return right from there, return false. But if we loop and we keep on looping and we keep on adding 1 to j, and we keep on dividing I by j, and we never get 0, we always skip out, eventually j is going to equal I. We're going to go all the way, if it's like 13, we're going to try 2, then 3, then 4, then 5, and we're going to go all the way up to 13. And if we hit 13 and we still haven't gotten a remainder of 0, then we know 13 is prime. And at that time, we can return, the while is over, and we can return true. Okay? So this here should give us our prime function. And to test that, let's just try some numbers. I'm going to try for I in the range of 2, how do you do range? To 100, is that? You do something like that, right? Let's do if is prime of I is true, then print I want to print the prime number. Okay? So this is just going to go, this is just going to loop from 2 to 100, and if the number is prime, we're testing to see if this function works. Then it'll print it out. If it's not, it'll skip this, and it'll loop up until I gets to be 100. So let's test this. I'm going to just do Python test.py. And here we go. We've got all these numbers here all the way up to 97. And these look like prime numbers. These look like prime numbers all the way up to 100. It goes up to 97. All right, so I believe this function works. And so we have this function now. This, I guess, is going to be the answer to this question where we're defining a function receives. So that would be the answer probably for that. But let's go back and try to do this previous question here now that we have a function we can try out. We have this is prime function, and we're going to loop adding prime numbers until we get a number less than or greater than this n here. So let's go back to here, and we're going to start. Okay, we've got this is prime here. We're going to total up. We're going to total up something. Start out with 0. We're going to look at prime numbers. Let's look at I as prime number. We're going to start at 2, and we're going to have to count. There's no semicolon after this. And we're going to count up how many times we're able to do this. And so we're going to do, let's see, we're going to look at while. I'm just going to call this sum. While the sum is less than or equal to a value n, we're going to loop while the sum is less than n. If, I'll put a colon there, if is prime of I, so we're looking at I at prime, we're looking at I, and I is going to be incrementing, looking for prime numbers. If I is prime, then we want to add it to the sum. Otherwise, and we want to count the sum. And then let's look at the next I to see if that one is prime. So while the sum is less than or equal to n, it's going to check to see if I is prime. If it is prime, it's going to add it. It's going to add the count, and then it's going to increment and look at the next one. Now, I think we could be off by one here because let's try. Okay, I have to read in an n. So let's we have to read in an n. Right here, let's do it here. N equals input int input n. Okay, let's see what this does. And let's make n 50. N is 50, sum is 0, I is 2, count is 1. Input n, while sum is less than 50. Oh, I'm not printing anything out, am I? So I'm going to print out, oh, I guess I'll just print this out at the end. Print sum, I want to print out I might as well print out count, I, and sum. Let's see what this does. 50. So count is 7, I is 18, and sum is 58. Let's see. I think the trouble is we're past 50. We want to count up all the ones up until we get to this. Up until we get to 50. What happens if we do 10? Yeah, 10 goes past. Let's print out count I sum just to see this, and I'm going to put, just so I can keep it straight here. What did I just do? And I think I didn't mess anything up here. And okay, we actually want to count is this. Okay, so count is the first one. So we actually want to stop at 3. We want to stop at 3 because 10, it hits 10, and we're supposed to go can be added before the total exceeds 10. So 10 is okay, but we don't want to go all the way to 4 because 4 would exceed 10. We need to go, can be added before. So so we actually want to do something like, we want to stop beforehand. Let's put sum plus I. So it will, so it should stop at, well, it'll stop at 5, I think. So it should stop one time earlier. It'll stop because once sum plus I exceeds n, then there's no sense going any farther because we've passed the point. So let me save this and try this. And if we try 10, then it stops at 3. If we try, let's try 16. Stops at 3 because if we add 7, it didn't stop at 6 because when we add 6 to 10, we have not exceeded 16. So it's not until we try 7. If 7 turns out as prime, but it's beyond the count, because 7 plus 10 is beyond 16. So so anyway, so this is what the code would look like, and we need to turn in k. K's got to be the count. How many prime numbers can be added before the total exceeds n? So we start out with a total of, start out with 2, and when we add 3, does it exceed n? If it does, then we stop. If 3 exceeds n, we want to stop at 2, and so on. So anyway, this number's got to be k. So we just want to make this k. And we actually don't need these prints in here. We don't need these prints in here because we aren't asked to print anything out. We're just asked to write this code here. We don't need this either because it will already have n. In fact, we don't need any of this either. It is this code here that we would need. So we're using this isPrime function. We're looping until we find sum. If sum plus I is less than or equal to n, let's try it. If I is prime, we add it. It'll still work because it passed this thing. And then we increment. And if this hit, then we've got one more added. And then we increment I, and we try the next I. And we do that until we try an I that we know will be too big, regardless of whether it's prime. We've hit an I, regardless if it's prime or not. It's too big. It'll be too big, so we're done with where we last incremented k. So something like this is the answer. All right, so that should try. You can try that out. We've done 7 here. We've actually come up with this function. The last question here is we have this isPrime function. We have a variable n. Same with the variable n. This time we're adding up prime numbers. Oh, this time we're just adding the first n prime numbers. So in the last one we were counting a different thing. So this time we only need to count each time we hit prime. We simply need to so we can have the same kind of code here, and each time we hit k is going to count, and and I will be the prime numbers. So and we're counting the first n prime numbers and adding them up. So the loop counter will be, let's have the loop counter be k, because that's counting. So while k is less than n, we're going to go from k goes from 0 to n minus 1. So that'll loop n times. So we'll find, okay, so we're starting out with 1 prime number, and k is equal to 0. Is k less than n? Let's read in an n. N equals int of input n. And we start out with we start out with this prime number, k equals 0. Is k less than n? Yes, it is. Let's say n is 10. Is I, which is 2, is I prime? Yes, it is. So we're going to add this prime number to the sum, and we're going to increment to find the next prime number. Oh, because we increment k because I was in fact prime. And then we increment I, we try it again, and if we test I. If I is not prime, then we are not going to increment k because we haven't found the next prime number, and we're not going to add that number to sum because it's not prime. So this loop is going to continue. When we find a prime number, we'll increment k. If we increment I, this thing is going to keep on looping where I is going to keep on incrementing, and each time we find a prime number, then we can increment k. So if n is 10, then k has got to be incremented 10 times before k will equal n, and the loop will stop. Each time k is incremented, we've found a prime number, and so that prime number gets added to the sum. So this thing can go on forever. It can go on to the 10th. So this number can get pretty large, and it'll stop. The loop will stop when we found 10 of them that are prime, because that's what this counter does. So let's try this code. See if this works. Oh, I got to print out. Let me print. I'm going to print k, I, and sum. So run test n. Let's try this again. N is 10, and we get sum is 129, and the last I was 30. So 29 was the last prime number because we incremented here, and then that's when k got we incremented the k here. We also did this, and so this will be done whether or not the last number we found was a prime number. So 29 would have been the last prime number. Let's print k, I, and sum, and let's make this be the end. And if you see what this looks like, n of 10, and we get 1 through 10. These are the prime numbers: 2, 3, 5, 7, 11, 13, 17, 19, 23. And each time we're adding, 2 plus 3 is 5, 5 plus 5 is 10, 10 plus 7 is 17, plus 11 is 28, plus 13 is 41, plus 17 is 58, plus 19 is 77, plus 23 is 100, plus 29 is 129, and that's the 10th prime number, so it equals 129. And we end here. We incremented I one more time, which is why this I ends up being 30. Like that. So this looks pretty good. We would not need this code. We would not need this code. We would just need this code probably here, and the sum should be associated with the variable total. Okay, so this should be total. And we don't need to worry about any of the other numbers, although this is n, this is n. All right, so that should probably work. Okay, so we have completed quiz 6.2 here, and so I will end this video and put it up and start and finish up the quiz. Finish up the quizzes for chapter 6 in the next video. All right, thanks for watching.